It's a pleasure to give this talk in this very nice online seminar. So, feel free to stop me at any time during the talk and ask questions. So this is based on more or less a couple of joint works that I've had with Katja Krupczyk in UC Irvine and Gunther Ullmann from University of Washington. And the topic of the talk is about inverse problems with passive measurements for PDEs, but this is connected to some multidimensional new types of multidimensional inverse spectral problems that I will discuss. But to just explain roughly what we mean by this terminology of active versus passive measurements in inverse problems, let me give you a physical motivation. Suppose you have the Earth and you consider two types of experiments. In one experiment, you proceed to create artificial explosions, or send arbitrary types of acoustic waves into the Earth. And as these waves that you send in travel inside, some of it will get scattered back naturally. And then on the surface of the Earth, you have placed a lot of seismometers and you get to measure these waves that travel back to the surface of the Earth. And then you repeat this experiment many, many times. You send in various types of arbitrary acoustic waves and you obtain all this data. And from all of this data, you want to image the interior of the Earth to understand how it's built. And for instance, where you can find oils or minerals, these kind of things. This is an instance of inverse problem with active measurements where you have an abundance of data and you can arbitrarily input something into the system. But of course, you cannot travel inside the Earth. This is why it's called an inverse problem. Inverse problem with passive measurement is a bit of a much more challenging problem where you cannot send an input into the system. But for instance, what happens is that there is some earthquake. And now this earthquake creates acoustic waves that travel to the surface and you measure these waves. So now you don't have access to even the input. You don't even know what is the input to the system. It's some unknown earthquake. And still you measure some measurements on the surface of the Earth. And now from this limited measurement, you want to reconstruct everything. The interior structure of the Earth and also this initial data, which is the earthquake and where it happened, what was the magnitude. So it's notoriously challenging because you have very limited data. Okay, so that said, let me now mathematically describe the main objects in the talk, which is more or less about evolution equations, second order evolution equations. And for this, I need to introduce the Laplace operator, which is this canonical second order differential operator, which is self-adjoint. So in this talk, we will assume that we are on a compact Riemannian manifold. It can be with or without boundary. If you like, you can just think of this manifold as a domain in Rn. But for instance, it can also be the sphere, the torus, so it can be a general manifold. All that we ask is that it is compact. On this manifold, of course, you have the well-known Laplace-Beltrami operator, which, as I said, is just a canonical, invariantly written second-order self-adjoint differential operator. This is the Laplace operator in local coordinates. Again, you can just view this as any type of second-order differential operator. And why this Laplace operator is important is because it appears in a lot of physical laws. In nature, for instance, you can also add a scalar zeroth order term, which we refer to as a potential. And then with these terminologies, for example, I've written here the laws of conductivity of electricity, the law of conduction of heat, propagation of waves, and also, for instance, dynamical Schrödinger equation, which happens in quantum mechanics. As you can see, all of these have this structure where, for instance, you do see this so-called Schrödinger operator appearing in the equation. Of course, evolutionary equations also have this time dependence. Throughout this talk, we will assume that this metric and the potential are independent of time. Okay, and what is also classical and well known, but I would need to set up the notation, is that for these Schrodinger operators, assuming that the potential is real valued, which is very physical, there is an orthonormal basis, L2 orthonormal basis, which consists of eigenfunctions of this Schrodinger operator. I will denote the eigenvalues with lambda k's in increasing order and the eigenfunctions as phi k. And these eigenvalues are real, increasing, and they don't have an accumulation point, so they go to infinity. Okay, so this is basically the notation that I'm going to use throughout the talk. And now with this notation, let me go back to just a couple of slides about these inverse problems with active measurements, because there has been a tremendous amount of research over the past 45, 47 years on these inverse problems with active measurements where there is a lot of data that you can use. And typically what it looks like, this inverse problem with active measurements, is that you have some manifold. Again, you can think of this as a domain. You have some partial differential equation. You are looking at the solutions to this partial differential equation, P of u equals 0. And then you have some observation region in this manifold. Typically, this observation region could be, for example, near the boundary, a neighborhood of the boundary, or it can even be on the boundary. And you get to know the solutions on the boundary or near on this set O. Okay. So again, in the example of the Earth, you can think of, this set O being the surface of the Earth, and this M being inside of the Earth. Okay, so we get to measure the solutions on this set O. And from these measurements, we want to reconstruct uniquely this differential operator P. Okay, it's a very challenging problem. And there are very few cases. So as far as I know, I've listed here 4 cases. There are very few cases where we have been able to answer this question very, very generally without any assumption. And this is why I've only written here 4. Otherwise, there could be pages and pages and pages of references. I just wanted to list some references where there is absolutely no geometrical assumptions. And the most well-known example is for the case of wave equations with time-independent coefficients. This is a result of Belishev and Kurilev, where this differential operator P is, the wave equation, specifically this equation here. This is completely well understood. Other evolutionary equations were also followed by reduction to this inverse problems for wave equations. This goes back to Kachalov, Kurilev, Lasas, and Mandash in 2004. In 2018, there was a result for very, very general nonlinear wave equations stated on arbitrary Lorentzian manifolds by Kurilev, Lasas, and Ullmann. And the key was this nonlinearity in the equation. And also more recently with Tuhin-Gush, Krupchik, and Ullmann, we were able to also address inverse problems with active measurements for fractional powers of Laplace-Beltrami operators. So these are results where really there are no geometric assumptions. But there are way more results for these inverse problems with active measurements, assuming some geometric assumptions. Okay, let me also say one example of an inverse problem with active measurements that arguably is the most well-known open problem in our field of inverse problems. And this is the anisotropic Calderon problem, which says, suppose this operator, this differential operator, is simply the Laplace operator. So you're looking at harmonic functions in a manifold. And you are saying that I know the harmonic functions in this manifold on some subset O of the manifold. Can I use this data to uniquely reconstruct the manifold? The metric, the differential structure, up to isometries. This problem is the so-called anisotropic Calderon problem, and it's the most well-known open problem. So this problem is completely open in dimensions 3 and higher. There have been some very classical results in the cases, in some particular cases, where the manifold, for example, is conformally Euclidean, is the seminal work of Sylvester and Ullmann. In dimension 2, it has been solved by Lassas and Ullmann based on prior work of Nachman. But as I said, it's widely open in dimensions 3 and higher, and we have no idea, more or less, about what to do. And this is inverse problem with active measurements. As you can see, we are talking about every single harmonic function. We know it on the set O. Okay, now let's go to, if there are no questions, I would like to go to inverse problem with passive measurements, which is the topic of the talk. So again, just to remind you, the situation here is that we want to study similar types of inverse problems, but this time we cannot make any inputs into the system. So here is a system that is completely unknown, such as a medium, and we cannot put any inputs into the system. There is some initial causal factor that created some kind of a measurement, created some kind of a data. We don't know what that input was, but nevertheless, we see some observations. We see some waves, for example. And from these measurements, we want to reconstruct everything. We want to determine what was this system, and we want to also determine this initial unknown, the initial data. Okay, so this is the setting of the talk. And to pick a concrete example, although the precise equation doesn't matter, I could have discussed a different equation, but because of connections to photoacoustic tomography, let me go with this model. So let's take the wave equation on a manifold with some scalar unknown potential. So here I've highlighted the metric in red, I've highlighted the potential in red. And as you can see, I've highlighted also the initial data for the wave equation in red to emphasize that all of these are unknown. We don't know what is the metric, this leading order coefficients. We don't know what are the zeroth order coefficient in this wave equation. And we don't even know what is the initial data. Now, some of you might say, why do you impose this zero on the normal derivative at t equals 0? That's not important. The only reason I added this to be 0 is that this model is inspired by photoacoustic tomography, and in photoacoustic tomography, this U is related to pressure of acoustic waves, and the time derivative initially is 0. And so in photoacoustic tomography, this is really the model. Okay, and let's say that if you have a boundary for your domain, you pose 0 boundary data. This would correspond to, I believe, a soft boundary in the terminology of photoacoustic tomography. So what is the inverse problem? The inverse problem is as follows. Suppose you have two such systems. I always refer to this as a system, So system 1 is metric G1, potential V1, and initial data F1. And there is a second system with, the second pair, G2, V2, and F2. These are unknown. But suppose there is some open set in this manifold where the solutions to these two wave equations match for all time bigger than 0. So the solutions that we observe are the same thing. Then can we say that the two systems are identical? And here I've put in this strange sign because typically you cannot prove that they are all equal. There is a gauge in this problem. This gauge comes from change of coordinates. So the best you can do, which is the optimal thing, is to show that these systems are equivalent up to change of coordinates. But I don't want to write it out, so I just put this equivalent sign. Okay, so that's the optimal gauge, and we want to ask whether we can really prove this up to this optimal gauge. Okay, so in other words, can we determine uniquely the system from the measurements of the solution on the set O? Okay, this is the problem that we want to study. And as you can imagine, this should be very hard because we cannot do anything, right? We just have some measurements and that's it. There's no freedom to input something into the system. Okay, let me say why this is related to some kind of an inverse spectral problem. Okay, and the reason it's related to an inverse spectral problem is you can, for this kind of evolutionary PDEs, you can always go to a spectral representations of solutions. So, for example, this initial data f for this wave equation, you can write it in terms of its eigenfunctions. So there is this eigenfunction expansion for f, which I will refer to also sometimes as the Fourier expansion for f. And then there are these coefficients, which I sometimes refer to as Fourier coefficients, okay, of the function f. And then with these notations, you can write the solution u spectrally. In the case of the wave equation, this equation in blue will be the representation of the solution. And then in this equation, you see nothing is known. We don't know what is f. We don't know what is the eigenfunctions. We don't know what are the eigenvalues. So we know next to nothing. But we know u when x is in the set O for all time. And so you can imagine by doing some simple complex analysis, like taking Laplace transform, studying its singularities, you can imagine that without much difficulty, this equality reduces to the following data, which is we get to recover some eigenvalues and some eigenfunctions. Specifically, we can recover some lambda k, one eigenvalue from each eigenspace. This is what I mean. And corresponding to that, we can obtain this expression, which is, all eigenvalues within that eigenspace, and then this sum. Of course, this is quite a bit ugly because we don't know what is f. We don't know what are the pj's. So what do we really know at the end of the day? We know some eigenvalues, and associated to each eigenvalue, we know some eigenfunction, like some general eigenfunction. This general eigenfunction is, for instance, not L2 normalized or anything, because within it, you see it incorporates the initial data. Okay, so to summarize, we get to recover some eigenvalues and some eigenfunctions, but these eigenfunctions, for instance, are not orthonormal. We don't know anything about their L2 norm. Okay, and the problem is kind of equivalent to this. Can we use this data to reconstruct the manifold and the potential? And already, if you go to dimension 1, you see that this has some implications, namely that you need to assume that the spectrum of the operator is simple, that the eigenvalues do not have multiplicity. Because already in dimension 1, if you miss eigenvalues, you run into trouble in a inverse spectral theory. Okay, so already there is these obstructions even in dimension 1. So it seems at the very least you need to assume, for instance, that the eigenvalues have no multiplicity 1. Okay, but this was, some motivation. Let me go to dimension 1 about these inverse problems with passive measurements. So let's consider the same wave equation, but on an interval. Is this problem well understood in dimension 1? And the answer is yes, this problem is well understood in dimension 1 because our understanding of inverse spectral theory in dimension 1 is phenomenally, rather complete, although there are, of course, important open problems, but we know deeply inverse spectral theory in dimension 1. So for instance, in dimension 1, one of the results that we know is that if this initial data and the potential V are admissible, what do I mean by admissible? I mean that the potential is, for instance, the eigenvalues have multiplicity 1, which, for instance, will be always the case if the potential is real value and you are on an interval. And secondly, this initial data f, again, is admissible in the sense that when you write f in terms of its eigenfunction expansion, every single eigenfunction is present. This is a generic condition, by the way. So under this generic condition, then namely that this f this orthogonality condition is never satisfied, so this f is never orthogonal to an eigenfunction, then the problem is well understood in the sense that if you have two systems, for instance, whose normal derivative of the solutions at the endpoints are equal, then the potentials are equal and the initial data are equal. For instance, this problem in the case of parabolic equations was studied a lot by the Japanese school. I've mentioned here three results in the case of parabolic equations in dimension one with exactly similar types of assumptions. In the case of 1D Schrodinger equations, I refer to Avdan and Mikhailov Ramdani for similar results for 1D dynamical Schrodinger equations. Even, let me also mention that, so a lot of these results in dimension one are for situations where you measure the normal derivative of the solutions at the endpoints. You can ask what happens if rather than working with endpoints, we work with some interval around an endpoint, okay? So let's say we get to measure the solutions from 0 to some number, okay? And let me say, actually, interestingly, this makes the problem even more difficult in dimension one. Namely, curiously, there is this phenomenon that even if you have this equality of the solutions from 0 all the way up to 1/2 minus epsilon, and even if the initial data is admissible and let's say the potential is real value so that the eigenvalues have simplicity, still we cannot solve this problem. You can construct two systems with the same measurements on this set O. This goes back to results by Hochstadt and Lieberman about inverse spectral theory. And also, let me say that when you're not working on the interval, when you're working on, for instance, the circle, the unit circle, instead of the interval 0 to 1, and pose the similar inverse problem, then this set O must contain two antipodal points. This is a result of Suzuki. So in some sense, if you're working on a closed kind of shape in dimension one, S1, for which you measure the solutions on some set O, this set O, interestingly, must contain 2 points which are farthest away from each other. Otherwise, you cannot solve this inverse problem. Okay, so these are already interesting things that one can see in these problems in dimension one, that even though we have very complete understanding, you can see some difficulties, namely that the set O somehow, if you want to have these sets O from one side of the interval, they need to be rather large, like half, which is interesting. Or in the case of this, the unit circle, the set O must contain 2 points that are farthest away from each other. Okay. So this is the, I think, a state-of-the-art results for inverse spectral problems in dimension one. Although recently, for instance, I've had also results with collaborators where we have replaced these kinds of assumptions with certain support conditions for initial data, where we can say, okay, we don't need to assume these admissibility conditions. All we need to know is some kind of information about the support of these initial data. And also some results on unbounded domains, which are very general. They don't impose any assumptions. Okay, so having said that, let me now state first result that we have with Katya regarding these inverse problems with passive measurements. I should say that in these multidimensional results, as far as I know, there have not been prior results in this case of, for instance, bounded domains. In the case of unbounded domains, there are certain results on inverse problems for passive measurements, but the assumptions are quite strong. Assumptions are some things like you need to assume that, you know, some monotonicity conditions, some very strong assumptions, or some finite dimensionality assumptions. So there are very limited results. Okay, so what are our results with Katya? Essentially, we want to generalize these one-dimensional results to multi-dimensions. So let me state our results with Katia, for instance, about wave equations, which is the model that I presented to you a few slides back. So we take the wave equation, as I said, with unknown metric, with unknown potential, with unknown initial data. And what is the setting? To make it easy to understand, let's assume that the manifold is just a domain in Rn. Let's assume that this set O, where we measure the solution, is just a neighborhood of the boundary. Okay? And then let's say we have two general Riemannian metrics on this domain with boundary. And let's say we have two general potentials, real valued. So what are the assumptions that I'm going to impose? I'm going to assume that the manifolds are simple in the sense that the geodesic flow does not have conjugate points. Okay, so essentially the exponential map is smooth. This is one of the assumptions that I'm going to impose. If you want to just have a concrete example, think of the matrix as being near Euclidean. For instance, that's completely okay. So that's the assumptions that I will impose on the matrix, unknown matrix. What are the assumptions that I will impose on the initial data and the potentials? Similar to dimension one, I will assume that they belong to a generic set. If you recall the dimension one, what it was, it's a similar notion. But anyways, this assumption that I will impose on the potential and initial data is a generic assumption. Okay, so topologically speaking, it's satisfied for most functions. Okay, under these two assumptions, we can solve this inverse problem with passive measurement. Namely, if you have two systems of wave equations and the solutions corresponding to these two systems are identical on the set O, and I recall that this set O is just a tiny neighborhood of the boundary, then the two systems are identical to each other, okay? So our measurements uniquely determine the system as well as the initial data, assuming that the initial data and the potential are generic, and assuming that geometrically the manifolds, satisfy some geometric assumptions, namely they are without conjugate points. Okay, so this can be thought of as a generalization of these one-dimensional results in the context of inverse problem with passive measurements. Let me also state a second family of results that we prove with Katia that have a rigidity flavor. So in a sense, they are stronger results because we impose our assumptions only on one system, our generic assumptions. Okay, again, to make it easy to understand, let me just give you three examples of what I mean by the manifold. For example, similar to the previous slide, you can think of the manifold as a simple manifold, again, like a domain with boundary, where the geodesic flow does not have conjugate points, and O is just a neighborhood of the boundary. Okay, so that is one thing you can visualize. Another thing that you can visualize is your manifold is the n-dimensional flat torus, the quotient of the Euclidean space with the integers. And O is just a neighborhood of the center and the corners of this torus. Another third example that you can picture is that, the manifold is a closed Riemannian manifold, such as the sphere. And O is the set O where we do our measurements is such that the complement of this region is simple. So let me give you a precise example. For instance, you can think of the sphere in our space and think of the set O as a tiny neighborhood of the equator, okay, or half of the equator. Okay, that would be, all of these are examples of the kind of manifolds that we can discuss. Now, what is the assumption on the initial data and potential? I will only impose the generic assumption on F1 and V1, okay? So in this sense, these results are much stronger because now I'm saying assume that F1, the initial data for system one, is generic, assume that the potential V1 is generic, but let me assume nothing about F2 and V2. But let's suppose that the two systems still create the same measurements on the set O. for wave equations, where f2 is any function that you like and v2 is any function that you like. This equality implies that the potentials are the same and the initial data are the same. Okay, so this is a truly uniqueness result in the sense of rigidity. Okay, and in this sense, in some sense, it's even stronger than these 1D results. Whereas the previous result is, you see, the generic assumption is imposed on both coefficients. But in this result, of course, I should also emphasize that we even recover the metric. Okay, so this is our new results on this inverse problem with passive measurements. And all of these results, all of these new results, as I said, are connected to some new inverse problems in a spectral theory that we formulate with Katya and we prove results for. Okay, so what are these new inverse spectral problems that we call inverse spectral problems with a sparse data? Let me formulate it in this slide. And let me say that, of course, still we don't have a complete understanding of these inverse problems, but we have some, of course, results on it. Okay, so what is the formulation of this multidimensional inverse spectral problem? We go to these notations that I described. So we refer to the lambda case as eigenvalues of the Schrodinger operator. I will always work with two Schrodinger operators because always I want to formulate some uniqueness problem, right? So we have two Schrodinger operators, then we have the spectral decomposition of these Schrodinger operators. And now what I say is the following. Suppose you have the full spectrum denoted as lambda k's, but suppose that I denote by phi kj's some linearly independent set of eigenfunctions, okay? So let me crucially emphasize here that these eigenfunctions that I will use in this formulation of this question are not orthonormal, okay? All that I require is that they are linearly independent, okay? So you can think of this as a Schauder basis for L2, okay? So we have the knowledge of the spectrum. So the spectrum is denoted with lambda k's, and we have some basis of eigenfunctions, but this is not an L2 orthonormal basis, okay? Okay, so now with this terminology, what is the inverse spectral problem? The inverse spectral problem is the following thing. Let me state it in a way that is easier to understand. Suppose instead of me saying that all the eigenvalues are the same and all the eigenfunctions are the same on the set O, what I know is somehow a lot less. What I know is that part of the spectrum of the first operator is a subset of the spectrum of the second operator. Okay, and this creates, of course, these indices. Because what I'm saying is that somehow you have an eigenvalue of the first operator, and this happens to also be an eigenvalue of the second operator. So, of course, the relation of the indices is completely unclear. And also, corresponding to those equal eigenvalues, there are some eigenfunctions that are equal on the set O. And these are just some eigenfunctions. We don't know anything about their global L2 scaling or things like that. Okay. So this inverse spectral problem then asks, can we use this equality to show that the two manifolds are isometric to each other and the two potentials are also equivalent up to this change of coordinates? Okay, that's the new inverse spectral problem that we pose. And as far as I know, in this language of working with just linearly independent eigenfunctions and going with this kind of subsets of the spectrum and mixing the indices, there are no prior results. Okay. Let me say that in dimension one, of course, there are some results on this problem. But also dimension one is highly special because in dimension one, of course, you know that eigenfunctions and eigenvalues are related to essentially zeros of some holomorphic function, entire holomorphic functions known as a spectral functions, okay? And essentially, eigenfunctions in 1D can be solved as a Cauchy problem. And that's that's the key point. That's why we understand it so deeply. Okay, so in dimension 1, of course, this problem has been studied, this inverse spectral problem that you see highlighted here in red. And before I state these results, let me say that in dimension 1, these indices do not create a lot of difficulty, because in dimension 1, our spectral asymptotics is rather precise, and we can write eigenvalues asymptotically up to any order of precision that you like. There is a spectral formula, asymptotic formula. So actually, AK must be equal to BK by just a while law. This is something that will not be true in dimensions 2 and higher. Okay, so these indices do not create a lot of problems in dimension 1. But regardless, let me say that the seminal result of Borg-Levinson, for instance, show that if all the AKs and all the BKs are equal to each other and all of them are equal to K, and if O is the endpoints, then this equality implies that V1 is equal to V2. There is the result of Hofstadt and Lieberman that says that, okay, if this set O is half of the interval, then we can recover the potentials. And this half is optimal in the sense that if this set O is less than a half, then this equality does not imply equality of the potentials. So that's interesting. You see already in dimension 1, something interesting is happening, that even if you know the full spectrum, and even if you know the full eigenfunctions, equality of full eigenfunctions, the very fact that these eigenfunctions are not orthonormal implies that this set O needs to be large. I just want to emphasize this because even in dimension 1, this orthonormality of the eigenfunctions is such a big deal that you need it. Otherwise, the set O needs to be rather large, which is interesting. Then there are further results. For instance, I refer to Gestazis and Simon, that if the set O becomes larger than 1/2, then you can drop parts of the spectrum. So this set AK could become less and less of the spectrum. Okay, so specifically, if you go to 1/2 plus epsilon, then roughly speaking, you can drop off 2 epsilon fraction of the spectrum. So the AKs could be less than just K. Okay, you can use less spectrum and use these identities to reconstruct the potential. Okay, so in dimension 1, we have a very good understanding of this inverse spectral problems, but the key is that our understanding is very much dominated by complex analysis and the fact that eigenfunctions in 1D are solved as a Cauchy problem, which really allows us to do a lot of analysis. This is not true, of course, in higher dimension. Also, let me try to emphasize why this orthonormality of eigenfunctions at a very, very heuristic level, why this is important, okay? This will not really tell you how we are going to get around this issue, but somehow I just want to say why this orthonormality somehow is important. If you take any function f that is supported in the set O, the set O is, remember, the set that we somehow know, right? The set O is where we do our measurements, it's where we are standing, it's where we know things. So let's have a function that is compactly supported in the set O, and let's write it in terms of its eigenfunction expansion. You see, if the eigenfunctions are orthonormal, and if I ask you, okay, here I give you this function f, can you tell me the coefficients, ak, you will say, of course. The coefficients are given as the inner product of f with the phi k's, and I know the phi k's on the set O, so I know the coefficients ak. But the key here was that these eigenfunctions were orthonormal, and that's why I can determine the AKs. If the eigenfunctions are not orthonormal, and if I give you a function f, and if I give you the eigenfunctions on the set O, can you tell me the coefficients? Of course not. And there's no way to answer this question. This somehow is a key issue in addressing this inverse spectral problem. That even if we know the function f, and even if we know the set O, and even if we know the eigenfunctions, these coefficients are a mystery to us. Okay, And now also let me say that even in multi-dimensions, the set O, because we drop this orthonormality, this set O needs to be, this set O cannot just be anything. So for instance, let me give you an example. Let's take this manifold M to be, the product space of the unit circle with the interval 0, 1, just a cylinder. And imagine you have two Schrodinger operators on this cylinder. So I'm talking about the surface of the cylinder. You have two Schrodinger operators on this cylinder, and assume that all the spectrums, all the eigenvalues are equal, and all the eigenfunctions on the set O are equal, where these eigenfunctions are not orthonormal. Okay? Does the equality of this full spectral data imply that the potentials are the same? The answer is no. And the set O, even if the set O is all the way up to almost half of this surface of this cylinder, the answer is no. Okay, so you see, even in multi-dimension, the set O cannot just be anything. And if you are, for instance, in the case of this cylinder with this product topology, the set O needs to be at least half by just thinking about those 1D results. Okay, so in multi-D, of course, there are similar obstructions. Okay, the set O, even if you have the full spectrum, what is the correct set O to pick? All of these are questions that you need to answer. Okay. So let me now say the results that we have with Katya on this inverse spectral problem that rather interestingly mimics some of the results in this one-dimensional results by Horstad, Lieberman, and Yeshtezi, Simon, Suzuki, these types of results. To state this result, let me precisely define what I mean by the antipodal set of a point. If I'm on a compact manifold, what I mean by antipodal set of a point, P, is this set of all points that are farthest away from this point P. Okay, so if you're on the sphere, for example, the antipodal of a north pole is a south pole. Any point has one antipodal point on a sphere. Okay, so that is what I mean. But of course, this formulation works on any compact manifold. Now, what is the results that we have, for instance, with Katya and Gunther about this inverse spectral problem is that suppose that, we have two unknown manifolds, and suppose we have some common observation set O in these manifolds, and assume that the complement of this observation set is non-trapping, meaning that the set O where I'm doing my measurements, any geodesic in the manifold must at some point hit this set where I'm standing. Okay, so geodesics need to come back to me, all of them, or rather not me, but this set O. Okay, so this is what I mean by this non-trapping assumption. This is the geometric assumption that we need to impose. And secondly, we need to assume there is some point in this set O such that the farthest point in the manifold again is in the set O. Some of you might say this, can you give me examples of concrete examples? Let me give you two concrete examples. For instance, if you have a domain with boundary, think of the set O as a neighborhood of the boundary. Then this assumption is true. Okay. Secondly, in the case of the sphere, think of the set O as a tiny neighborhood of half of the equator. Okay. Then again, this will be true. Okay, then we can solve the following inverse spectral problem, where if all the eigenvalues are the same and some basis of eigenfunctions on the set O are the same, then the manifolds are isometric. The key here is that these eigenfunctions are not orthonormal. Otherwise, if orthonormality is assumed, this goes to the famous inverse Gelfand problem in higher dimensions, which has been solved by Belishev and Kurilev. Okay. Let me state a second type of result for these inverse spectral problems where we now use less data. This is a result with Katya, where we now discuss recovering not the metric, but the potential only. But this time we can now reduce knowledge of the spectrum. Okay, so I'm going to assume the same kind of assumption, a geometric assumption. on the manifold as in the previous slide. I'm going to assume that I have two different potentials and the same terminologies. But this time, you notice that I'm going to assume that I know a lot less. Namely, from the first spectrum, I assume that I only know some eigenvalues starting from some arbitrary number, capital N. So an arbitrary number of eigenvalues could be missing, but finite. And secondly, these eigenvalues are simply a subset of the spectrum of the second operator. So a priori, okay, these eigenvalues appear in the spectrum of the second operator, but the second operator could have significantly more eigenvalues, okay? And because of the while law in multi-dimension, this really actually is going to be significant, okay? And if we have these equalities, can we say that the potentials are the same? And the answer is yes. Okay. Finally, let me say that we also have results where rather than a finite number of eigenvalues missing from the first operator, an infinite number of eigenvalues can be missing from this first operator. So I don't want to go to the details of technicalities, but in our work, we have a precise terminology of how many eigenvalues of the first operator can be missing. And this goes to some notions of upper density and so on and so forth. But let me say, for instance, it's always allowed a logarithmic portion of the eigenvalues of the first operator to be missing. Like if you're going from 1 to n, a logarithmic portion of the eigenvalues could be missing. Okay. And secondly, to state this second result, we also need some kind of a uniform observability estimate for eigenfunctions, namely that we need some kind of estimates that says that in this set O, where we are doing our measurements, we need to be able to say that the global L2 norm of eigenfunctions is going to be uniformly bounded from above by the L2 norm of the eigenfunctions on the set omega, for any set omega in the set O, with some constants that only depend on omega and not on the frequency. Okay, so this is the price that we need to pay if we want to drop infinitely many also eigenvalues of the first operator. But let me say that these observability estimates are a very active area of research for instance, fractional uncertainty principles and study of chaotic systems. And for instance, it is known that this is true for the flat torus. It is also known to be true for Anosov Riemannian surfaces. This is a seminal result of Dyatlov, Gina, and Nonnenmacher. So these are, for example, Riemannian surfaces of negative curvature. But it's also conjectured, and this is a big conjecture in this field, that this is true for Riemannian manifolds of negative curvature, this estimate. But still, it has not been proven, although there have been some recent promising breakthroughs. Okay, so what is the result in this setting? Okay, if we allow this notion of eigenvalues to be missing from the first operator, so you can think of it as a logarithmic fraction of the eigenvalues to be missing. And if we have these observability estimates, uniform observability estimates on eigenfunctions on the set O, for example, these are two examples in which these are satisfied automatically, then we can even drop infinitely many eigenvalues of the first system and say that, if part of the spectrum of the first system, and here we could be missing, a logarithmic portion of the eigenvalues, is the subset of the eigenvalues of the second system, and then you have the same equality of eigenfunctions, then the potentials must be the same. Okay? So basically, these are the three inverse spectral results that we have proven. And these inverse spectral results are the key to addressing these inverse problems with passive measurements. Okay, now, initially, I thought also I would say a little bit about the proof, but I think that will really push me quite out of time. So I think this here would be a good place to stop because I've stated all the results and some intuition about what these are about. Okay, so maybe I'll stop here. Thanks for your attention.